So we are going to talk about this thing, and us is me, Nikolai Kondrashov, and Michael is sitting here. He'll join me later. Neither of us does actually look like that anymore. So we are coming from Red Hat CKI team or CKI project, and we're a distributed team which are doing kernel CI at Red Hat. So why do we need kernel CI? Well, as most of you probably know, we do releases of distributions, and each release has different kernel version. There's a lot of kernel versions, and moreover, we are one of the major contributors to the Linux kernel, and certainly the biggest one among distributions. So this shows the comparison of unique email addresses from SUSE, Red Hat, and Canonical contributed to the kernel, and this is commits. Each of those is per year, and the Red Hat is the blue one. So we somehow gotta make it consistent and reliable. And if you look at this, this is a big queue of how code goes through the pipeline towards Red Hat. And until not so long ago, our tests were only there at the end. So the developers would throw the commits over to, throw the builds over to the QA, and they would test it and then come back and they would retest it. That takes a long time. And if you consider how long it takes for the whole code pipeline to execute one patch, to digest the patch through that and get to a release, it's a long way. So what we want to do is we want to do this. And we want to do it fast and provide as much and as fast as possible feedback, so that ideally the bugs are caught before even maintainers see them at the moment that the developers submit those. And that is hard because there is just so goddamn much email. I mean, look at this. So we somehow are supposed, like, I'm not having anything against this message. It just shows the complexity of these things. So somehow we are supposed to put our webhooks in here. Like, this is patch number 62 out of 114, and there's this amount of discussion going on. So somehow we are supposed to test those and provide feedback to developers. So this has been an ongoing discussion recently in the kernel circles, and for example, the last Linux Plumbers, there was one of those presentations that are happening recently by Dmitry Vyukov, who did a very good take on those issues, and I recommend you watch it if you're interested in the kernel development process. He makes good points. So what we've built is something like this. This is simplified. And I actually lost a slightly more complex slide on the plane here because of how slides.com works, but never mind. This is very simple. And we'll go around. So normally, if you want to check just the changes in the Git repo being committed there, that's kind of easy. So we have a bunch of repos we track, and we check like if there are new commits, and we test those. That's fairly trivial. We actually have inside Red Hat, we have a bunch of Git repos for different releases like RHEL 7, RHEL 6, RHEL 5, RHEL 8. And we also track upstream repos, mainly stable at this moment, but we track also a few others. And we test those commits, of course, and that's relatively easy. We just pull the repo, and we run our test, about which I'll tell you a little later. Then there's the interesting part which I started with. Turns out it's not that hard. So, well, it's hard. It's hard. Don't get me wrong, but you can do it easier. So there's a typical mail list, like Linux USB mail list. There's a message from a series. It looks like this. Turns out there is a project called Patchwork, probably many of you know, which is used by maintainers. Well, most of all, they use it to track the patches as they're being processed, reviewed, and tested, and they check like which patches were merged and which not. So it looks like this. If you go to patchwork.kernel.org, there's a bunch of projects, and those projects can be mapped to a particular mail list or even a particular tag being used, like tag in the subject being used in the mail list. Well, at least at Red Hat it's done this way. I'm not sure if that's upstream actually. So if we go to the same Linux USB mail list here, you can see there's again those patches, but this time they're organized into series. And if you click on one of those links, you get to the particular patch series. There are 2 patches in there. We can go to specific patch and see like what's been going on, what's the patch, and we can download the mbox there on the right or the whole series. And the main thing that concerns us about this is that Patchwork has REST API. So we can go through those projects, we can extract the patch series, the patches and everything, and we can track when they are appearing. This is, of course, like sounds very simple, but the devil is in the details, where you have to kind of expect that not all messages come through at the same time. When you go check, and the series might not be complete, there are bugs, there are people sending all kinds of messages in there, sometimes they're not picked up, and things like that. Patch series can have cover letter, don't have cover letter, and things like that. But you can make it work. So the typical patchwork trigger would be tied to a particular patchwork instance and particular project there, and associated with the corresponding Git repo. Further on, we also have triggers from our package builds in Koji and the developers builds in Copper for Fedora and internally for RHEL, although it's called a little differently. Pardon, let's go back. So Fedora build system looks like this. There are a bunch of packages. They are being built, prepared for releases and reviewed. So we can look for kernel. There's our kernel. Let's take this one. And here's information on the build of the kernel, like specific revision and everything, and all the packages that were built for all the architectures. And Copper looks like this. Oh, wonderfully. Finally connected. So Copper is more for developers. You can have your package built and put into our RPM repo and picked up by your users or by other developers, and we track those as well. So you can look for the /kernel there and find one of those, and go in there and into builds and see there's been a build, and here's the packages. But we don't talk through the web UI, of course. There's the packages. We listen to the Fedora message bus, which is used both by Koji and Copper, and internally at Red Hat. There is a message bus as well. We just listen to the message. There's a log from our trigger, and it checks like, okay, there's build completed, there's a message coming through the bus. We're not interested in this one, neither in this one, but here there's the kernel. We pick it up and we trigger our pipeline. So we also have to test our own CI. So we have a special kind of two special kinds of triggers for GitHub and GitLab for testing contributions to our CI repos, of which we have many. And as you can see, we have some on GitHub and some on GitLab because of, well, historically. So it looks simply like this. You submit a PR or MR, and the bot comes and says like, hey, I'm a bot. Send me a message and I'll test this for you. So the developer says like, a test please, bot. And bot says testing, and you go. Then it triggers the pipelines through for the various repos that we have. A developer can go have lunch or two, and then it finishes, and the bot says like passed or failed. Well, as it happens, here's an example of my pull request. So the bot comes in and tells us like, here I am. This is what you can do, and it's a little different for GitLab and for various repos, and can say like, oh, add this keyword or that keyword, and we'll test this and that and things like that. And yeah, I am asking the bot to test. So the bot says, yeah, I'm going. Then it's posted the result. It failed, of course. So that's how we do testing for our CI, because many repos, and because our CI is in a separate pipeline, and we internally have 2 GitLab repos actually handling this, but about this, not repos, GitLab instances. That's a complication, a fun one, yeah. So further on, these are 2 major parts of our pipeline. Of course, the test database and the tool which lets us pick which tests to run and organizes everything into trees. and other dependencies like what we can run with this build, with that build, on this architecture, on that architecture, and etc. Whether developers want to test this or that. So basically, the data flow is very simple. We have kpdb, which is a repo with the test information, which is currently private because there's like all kinds of stuff for real internal ones, and we are still intending to open it up, but it's difficult to separate the upstream tests from downstream tests in a complicated data structure and somehow merge it together. So we have the database, which is basically YAML, and we have a tool which takes it and a bunch of parameters and then spits out the XML for bigger system, which actually runs our tests. And this system is installed internally, but it's open source, but you will have a very hard time actually trying to install it, which we are working on right now very hard, and hopefully we'll be able to let you guys enjoy it. But it's all open source, it's out there, including documentation. It's just nobody succeeded installing it by themselves yet. So the database can contain like information about architectures again, of which there are 5 right now. Kind of host types, and these describe what do we want the host to have. Like, do we want to have this much RAM, or this many CPUs, or this much storage, or even a particular PCI card or a network card, and we organize them into host types because that's easier. We have trees, obviously, particular repos or types of repos we want to test, and those affect which test will run where. Like, for example, one test can run on RHEL 7 but not on RHEL 5. And some on upstream, and some tests are still internal. Not many, though. Most of them are actually out there. Components which describe what things the build contains. Like upstream only contains kernel image, but internal builds, they're built using RPMs, and there could be debug info, headers, the internal kernel headers, and things like that, or tools that some tests need, like for example, some tests need debug info and things like that, or some tests don't run on debug build. So, and then we organize tests into sets, of course, like for network tests, for file system, memory, etc., virtual machines. And of course, the description of the test suites themselves, of which there are quite a big number, soon to be 100. And these are range from simple tests, like just a shell script, which just restarts the kernel, tests something, and it's done, to very big ones like LCP, USEX, and the top ones are listed there, I guess, but those are not all, which can contain like thousands of tests. So an example of test suite data, like a description, where it is in the repo. It's actually quite outdated. Anyway, the essence is there. Where it is located, and for example, this one is in our test repository on GitHub, where most of our tests are. Which host type it runs on, additional information of like, I want like this very specific host for this, like, and it could be down to a specific host name in our bigger system. Like, I want to run it like exactly here on this machine because there's only this hardware there. Which this description could look like this. Actually, this says, don't run on these ARM systems because they don't work. So information on maintainers, and this is a discussion for upstream. Let's leave it at that for now. So these are test maintainers who look after the test and check that it's working and it's failing, and they actually receive copies of failure reports, and they're supposed to take a look at as soon as something happens and tell the developer, okay, sorry, that's my bad, it's a failure, or say like, this is your problem. And they are responsible for those tests, which is going to upstream important because upstream developers, they don't see that much into our machines and things like that. So they have a hard time figuring out what actually happened, which we are working on. So there's the conditions for the test to run on, like the sets which it belongs to. And this is also outdated, my gosh. This is also an interesting part, that we specify which source files the particular test covers, more or less, so that we can avoid running it when there is a patch that doesn't touch those files, and that's why we can kind of contain the runtime at least a little bit, make it shorter when we don't need it. And this allows us to kind of describe when to run them for which code. Architectures the test would run on, and which trees it belongs to, but there are no components here because this is old. And could be like multiple cases of this repo. I wanted to run it with this file system or with that file system, for example, a file system test or additional parameters. And invoking the KPET tool, normally people don't invoke it by hand, but it runs in the pipeline. So you can say like, okay, generate me the XML for this run, for this kernel tarball, for the upstream tree, AR64 with this patch, and highlight the output, and it would look something like this, and it goes on and on and on. I'm not going to bore you with those details. This is the input to Beaker and saying how to run it and where to run it and in which order. So going to Beaker, it's a big system which maintains inventory of all the hardware, including down to the components. Lets you match that hardware, has access control, like particular groups have access to this hardware, those to this hardware, and for example, some NDA hardware could be there and protected. It also does the provisioning and boots up the machines, installs the operating system from scratch using an account normally, because we don't support running from images, because that's hard to do, and we are a distribution, so we have to test the whole distribution from install. So it installs everything, it talks to the test harness, extracts test results and things like that, and looks after the machine so that if it does lock up, then it releases the machine and erases everything. So it could be like the system inventory. We can find those machines, like these are not very useful right now. This is Itanium. We still have those. You can go into machine and take a look at the details. Like this is just one tab about the host information. There's the CPU info, storage, peripherals, things like that. And this is an example of some of our jobs running for stable repository of the Linux kernel. This one job is just for one architecture, and it has 4 hosts, and here's an example of one host executing those tests. This is a Beaker UI. This is a bunch of tests there. Further on, now we're approaching the user visible stuff. So we have a reporter which watches over the pipelines and checks which stage they're on, which job they're approaching, and sends the email reports to developers or whoever is interested. And sometimes it can send an early email saying like, okay, you have restarted this test, and like, watch out, or where you did the test, and or something failed in the pipeline. So there's an example of a successful report that was sent to a stable mail list. Here's it starts with the saying like, we took this repo, we took this commit, and there's the summary, everything went fine. And we were actually compile and use those commands. And then we run them on these hosts. So like this architecture is ARC64, first host, second host, PPC64, 2 hosts, x86. x86 got more hosts, 4 hosts. And we also have a notion of waived tests. A test which you mark in that KPET DB and saying this test is waived, which means run this test as normal, maybe at the end of the run, but ignore the result and don't take it into account when giving a verdict. Whether it failed or not, we say we ignore it. And we use this to test the tests which were just introduced into the system or were being fixed, so that we can track like how are they performing, like are they doing okay, and the test maintainer can look after it until it stabilizes. Then we remove the waived status. And this is done manually because tests are different. You have to look after them. And that's an example of report that we send upstream. Our internal reports are a little more elaborate. You get to see actually links to the Beaker results and explore the logs and everything. But those tests actually have, artifacts. There's a blue link there. These contain the binaries, config files, and logs, things like that. So, and then finally we have the data warehouse. It's a system which uses PostgreSQL and collects all the information about our runs, also similar to Reporter, and it's kind of duplication of the effort at this moment, but we are working on that. So it watches over all the jobs and collects some information like how it went and what's the status and which tests run. And there is a web UI which looks something like this and provides statistics, how much we failed, how much we succeeded. There's pipelines and various statuses. This is being pulled like from GitLab using the GitLab API. And there's a particular pipeline and listing all the tests and all the hosts, and you can go and see the results in Beaker, how it went. And we maintain the test statistics, how tests were failing or passing, for example, for exactly for the purposes of deciding like when to waive the test if it's been doing bad, and then send it back to the maintainer and say like, okay, deal with it, or we can actually take it out of waive state if it's doing okay. And same for hosts, like if some hosts are misbehaving in Beaker, and that's a problem because there are just so damn many hosts that they break, and you have to watch out, and the host maintainer, like whoever maintains that host, they don't have time to look after it. So we look at those and we say like, okay, this host should be excluded from the runs, and we add like, don't run on that host. So finally, the title of this talk, no, not yet. This actually concerns Guillaume's talk. So there is this thing, you probably seen it at the last slide. It's the kernelci.org, and they run lots of tests. And they were recently approved as accepted as a Linux Foundation project to advance the state of kernel CI. And we joined that effort. And right now we're working on a database, and the system used to aggregate testing information from various CI systems, so that the ultimate goal, so that there is a single place to go and check kernel CI results from whoever runs those tests, and so that the developers get only a single email with those results and not just 5 emails from everyone. Right now, this is mostly the kernel CI folks and us, but others are joining. Hopefully soon we start aggregating more data. But we already have a tool. Well, you can take a look like how this looks. I don't know if Guillaume showed this, but this is an example of how the test reports, like top level, could look there. So we took a Google BigQuery system for storing those results so they are more readily publicly available. And so that people can go and explore the data and see how kernel is doing and do research if they need to. So this is our repo with the code for that, and it looks something like this when it's pushing, and it's the data, and we are working on a dashboard to show this off and to provide the developers. This is very rudimentary at the moment. So finally, the interesting part. It took a little while. So we store our CI pipeline inside the YAML, but we store it in separate repos because of the way we trigger those. So to trigger GitLab, we're actually doing commits to the repo, and I'll show that in a moment. So basically, these are 2 repos, and the repo on the left is only including pieces from the other repo. And this lets us to let the triggers do commits with the information about what we want to test inside that repo. And we need two repos so that these commits don't interfere with the development commits we have. So because there's like every time you want to test something, there is a new commit. And that's an empty commit, and it doesn't have any data in it. So we use it just to identify the particular pipeline in GitLab view. So for example, the baseline trigger, like the Git repo trigger, comes in and does and sees that there are two changes in the like in one repo and another, and does commits to separate branches in that repo. This trigger actually is retired now, but it was quite kind of interesting. So it also does and checks and finds something and does the commit. There's the trigger that finds patches and does commit in that the same branch, and finally the GitHub bot comes and finds like, okay, there is a new merge request, and I put it in all the branches that we're interested in testing. And it might look like this. For example, the stable branch has those commits all with the pipelines running, and this branch has its own commits here. And the commits can look like this. So there is data there, but it's not for GitLab's consumption, only for us as debugging. Like this says all the variables that we put in there, all the descriptions, like what we are triggering on, things like that. This one is huge, and this one is big as well. It's abbreviated. So we use a lot of GitLab extends property, which lets us separate the general pipeline into a menu of jobs and stages, and into tree specific information, or pipeline specific information. This is our shortest pipeline, and it says, okay, pick those 4 stages from the pipeline, and we have 10 maybe or more. And this says, okay, pick this prepare step where we download all the stuff for the execution, all the dependencies, and this says like this is the prepare, and this is stage prepare. And this one we say, okay, again, pick this create repo x8664 and extend it. And this is one of those saying, okay, take this repo, take this template of the job and a bunch of variables and conditions, and create a particular job for this specific pipeline here. And this time we are using the merge keys to merge those. So we're using extends here because this is a separate YAML file, so we cannot use merge keys. And we use merge keys here. It's the same one big ass YAML file there. And this would be a create repo, creating a RPM repository with build results for testing, which are then installed in Beaker. The next stage is composed a little differently, so we have a huge script which is split into a few YAML objects. And finally, the last stage looks similar to that, and so on. So we have pipelines which are much longer than that and more involved. So why we took GitLab? Well, we started out with Jenkins. So we had a Python script controlling Jenkins, which had a job written in Groovy, which controlled another Python script, which checked out the kernel and built it and then fed it off to Beaker. So that was not very reliable, hard to debug, hard to understand, hard to maintain. As a contrast with GitLab, we had a relatively straightforward system. We could keep everything in the Git repo and keep changing it faster. And well, still, it's more reliable than Jenkins for us. And I hope Michael is able to say something. We have 10 minutes left. Okay. Maybe you can hold.
So now you will hear me complaining about GitLab, but yeah, I figure out. Anyway, okay. So I don't know how many people use GitLab here. Yeah. And how many people have used GitHub? Yeah. Okay. So it's very familiar system. So it's nicely documented. It has a huge API surface. People are familiar with it. So if I say GitLab, people actually know what I'm talking about. If I mention some other CI technology, then people look at me like this. If I mention Jenkins, people just go away and say like, no, you don't want to be on your team. Hopefully there's nobody from Jenkins here. Oh, sorry. But then we are actually testing kernel. So that's quite similar to other software to test in some aspects, but for other aspects, especially like testing, there are some interesting issues that you will see there. So one is that actually GitHub, GitLab, most of these general CI systems don't have any concept of a failed pipeline because of infrastructure issues. So if you look into what distributions do for gating, most of those actually have a test fail thing, maintain or fix it, and then they have something like, oh, our infrastructure failed or our test system, and then it's actually for somebody else to fix. Now, most of you might know that kernel maintainers don't react too well if you email them without any good reasons, or if you email the Linux kernel list with infrastructure issues, they get pissed quite easily. So we really want to avoid that, and that is not very easy. So you actually need to put stuff around GitLab to make that happen. On the slide on the left, you see what the test system actually gives you, which is Beaker in our case. And then there's this one missing. So a panic code in Beaker is actually the hardware messed up, the kernel didn't boot, but for whatever reason, or distribution didn't boot, or there was some power surge or whatever, or actually we messed up, or our general infrastructure had the networking issues, stuff like that. And that's not in the system. Might never get in there because it's not something that you would normally have for your average.
A little bit about that. Yeah, sorry. So one consequence of that is that GitLab. Yeah. Okay. Sorry. This is the line. Sorry. So the thing is, GitLab has infrastructure issues. GitLab CI has infrastructure issues, and you can select, okay, you can restart on this failure, on this failure, on this failure. But it actually doesn't matter to me which failure GitLab restarts on, because it's GitLab's thing. It can fail on various things, but it doesn't allow me to tell, like, okay, restart on this issue or on this issue. I can only say test passed or failed. And that probably comes from where GitLab is intended to be used in. It's like a test ran and nothing can happen. It's just running tests on simple software. But for us, if you remember that job, like just one architecture, 4 hosts for one architecture, and there are like 2, 3, 4 architectures more than that. And what GitLab does is they just kill us. Yeah. And that stays there. And that's a separate slide. I'm confusing the issues. But basically, we cannot tell GitLab, okay, we had an infrastructure issue. Can you restart? That's a big deal for us.
So, I mean, there are more interesting things. We actually, that's from the beginning of January, we are producing 30 gigabytes of artifacts a day, like kernel builds, RPM builds, all kinds of stuff. And if you use a shared GitLab shared GitLab instance like GitLab.com or whatever have you in Red Hat, we have a couple of those. People might not have the storage available. So you would want to store it outside, like in S3. If you build in the cloud, you want to keep it there. You don't want to incur the transfer costs moving it in and out, which is not possible at the moment in GitLab. So you can configure per instance, but not per project. And it all goes on like these things. So there are certain things where it doesn't really match very well with kernel testing, and you try to work around it. So it's possible, but it gets more ugly. So you can take a look at the code. It's on GitLab. Don't blame us for however we did it. It's really hard to upgrade because if you have like pipelines running for a day, if you do an upgrade, the GitLab runner will stop to accept jobs, so then you don't get any builds, any tests for a day. You can work around that, upgrade different runners at different times, stuff like that. What else do you have? We just skip down. Oh yeah, and that's an interesting one. Most test systems don't expect the test to reboot. So I don't know why, but kernel tests actually reboot a couple of times. It's like it's something that kernel developers think is useful. So if you need to boot into your kernel, but then you might also restart a couple of times in there. So you can't really have your test harness, like the GitLab part, have itself restarted. So you need to have another indirection. You just start another VM or have the GitLab part outside of your testing system, in this case Beaker. But otherwise you could just put it inside of your hardware lab, which you can't do at the moment. Yeah, maybe we stop here and take some questions. Otherwise I just complain about other bugs.
Let's take questions. 2 or 3 minutes for questions.
I don't know what kind of questions.
Yeah.
How much reproducing all the CI speed up the process? How much time did you gain with this? Before you had it and now when you have it?
Now the question is so the question is how much time do you actually gain from having CI? And I think depending on who you ask, there might be a different answer. So developers might most likely say like it doesn't help us at all in the beginning, especially now, where you might actually get infrastructure issues giving you false positives. But I think we find a couple of issues a week. Where
actually 4 maybe.
For a week. Where kernel developers were really sure that they got it right, but they didn't.
And that could be patches posted to the mail list, or it could be something merged into stable, for example, into stable Linux.
The ultimate goal is actually to free resources inside of RHEL, because upstream patches broke. So we want to provide feedback outside of it that it never actually goes through the whole pipeline. Now we'll only find out about it when it's already merged and built into an RPM. The ultimate goal is to have work done upstream, which you most likely said. Okay.
So you mentioned you were running Jenkins before you migrated to how painful was the migration and what strategy did you apply? Like, did you keep both instances running at the same time for a period of time, or did you just hard switch from one to the other?
We just rewrote everything and then switched. Yeah, the question was how painful the migration was. Like we took some of the tools that Jenkins was using, and we used them in the new pipeline, but we rewrote everything that was in Jenkins there, because you can't really run that in GitLab. So we had to rewrite a big part, and we had to rewrite the triggers and things like that. We replaced the separate tool which was controlling Jenkins with those little triggers that I showed you. Any more questions? Yes?
Is GitLab working on those issues?
Yeah, some of them. Like I think
The question was, is GitLab working on those issues? So there is an issue that particularly pisses me off, is that GitLab simply kills the runners. Yeah, there, this one. They simply kill the runners with sick kill. So for us, it's a runner that's controlling that bigger resources like this. I don't know, 10 hosts that are running those tests for hours, and we just forget about them because of that. Like GitLab just forgets, like, oh, whatever, and that host is occupied for these hours, so we cannot clean up. And this bug was open for years, I think, and they're promising they will fix it soon. So I hope they will.
there's somebody working on it.
Okay, our time is up, so catch us in the corridor.